Welcome back to Applied Physics. In this video, I want to introduce you to the concept of vectors. Vectors are an incredibly powerful mathematical tool that we're going to revisit several times throughout this course. For right now, I'm going to look at the most simple case of working with vectors so that we can focus on the mathematical tools necessary for dealing with them. So what is a vector? Most of the quantities that you have dealt with prior to now have been what we refer to as scalar values. Scalar values are represented by their magnitude. Things like time and temperature are classic examples of scalar values, as are lengths and widths, areas and volumes. The contrast to that, a vector is represented by a magnitude and its direction. Positions of objects are, I think, the simplest vector quantity to understand. If I am in our science hall in Youngwood, I might tell you that the administration office is in Founders Hall, which is 500 yards away. It might be more useful for me to tell you that it is 500 yards down this path heading northward. So telling you which way you have to go is just as important as telling you how far you have to go in order to talk about a vector. Mathematically, the ideas are a little bit different. In the mathematical construction of vectors, my brain usually relates them to coordinates on the coordinate plane. So if I have a set of coordinate axes here, and I have some point that I care about, let's go this, it looks like I drew the point 5, 3. So we'll go ahead and talk about that. So 5, 3 is the point on the coordinate axes where we are trying to get to. And if we start at the origin, that's not the pen I wanted. That's going to work a lot nicer. If we start at the origin, going from the origin to the point 5, 3 can be represented by this, this arrow. We'll go ahead and call that arrow R. And I'll put an arrowhead above the symbol R to emphasize that this thing is a vector symbol. We can represent this vector R by using angle brackets and listing the x component, which is 5, and the y component, which is 3. And as soon as we get to this point, students tend to ask me, what's the value of this? What does this give me that just the coordinates didn't? Well, the difference is when we're talking about coordinates, we're talking about the value of x and the value of y. And the reference point is always the same. But what if I had not just one stop, but 2 stops? Let's go ahead and call this R1. And then let's say that after I got to the point 5, 3, I needed to continue on to this point over here. This is the point, what is this? 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like I drew. 2, 9. Well, to get from 5, 3 to 2, 9, I go that way. We'll go ahead and call that R2, the second vector. And the components here, it's not 2, 9, because I'm not going from 0. I'm going from 5 to 2, which means I have to go -3 in the x direction. I'm going from 3 to 9, which means that I have to go a distance of 6 in the y direction. I could have shortcutted all of that and taken the straight shot. My vector s here is just 2, 9. And I can represent that algebraically by saying that vector s is equal to vector r1 plus vector r2. And again, if you think about these as positions of objects, maybe on a map, right? Thinking about how you are traveling, going point by point, these values are probably distances, all with units of meters or miles or whatever it might be. There is a physical reason that we might care about these. Okay. Mathematically, this is fairly straightforward once you get the hang of the notation. Practically speaking, we don't talk this way. Right? If I'm trying to give you directions from Greensburg to Pittsburgh, I don't tell you to travel 20 miles west and then 10 miles north. I tell you to go straight line in a northwest direction. So we need a better way of talking about how we actually talk about things. And the answer for that comes from the definition itself, a magnitude and a direction. Let's say we have a new vector. I'll go ahead and call it vector r because I like the letter r. And I want this vector to be a total distance traveled of, let's say, 25.0 meters. And I want to travel this direction at a heading of 75 degrees. Right. Once again, we have to agree on how we're going to talk about our headings. We're going to stick with the conventions that are commonly used in mathematics, not the conventions that are commonly used in orienteering. And the conventions commonly used in mathematics are that we always measure an angle in the counterclockwise direction starting at the positive x-axis. So here's my 75-degree angle, and here's my 25.0 meters. And then here is the point that we end up with. Now, if we think about how points on the coordinate plane are represented, the x component, I'm going to call it r sub x, so that I remember this is the x component of a vector r, and the y component, r sub y, can be drawn looking kind of like that, right? You have to go over some distance and then up some distance to get from the origin to the point in question. And those two components are at right angles with each other. This is a right triangle. I know it is a 75-degree angle. I know it is a right angle. And I know the hypotenuse is 25.0 meters. With that information, I can do some triangle trigonometry. I have an opposite leg, an adjacent leg, and a hypotenuse. I know that the sine of the angle is equal to the opposite leg over the hypotenuse. And if I plug in that my theta is 75 degrees, my opposite leg is what I've called ry in the original figure, and the hypotenuse is the total magnitude, 25.0 meters. I can rearrange this and get that ry is 25.0 meters times the sine of 75 degrees. My calculator is very happy to tell me that 25 times the sine of 75 is 24.148, etc. I guess I have 3 significant digits, so I'll call this 24.1 meters. There are rules for dealing with significant figures for angles, but I'm just going to stick with, this had 3 significant figures, so I'll go with 3 significant figures and I'll call that good enough. Very similarly, I can figure out that Rx is going to be that 25.0 meters times the cosine of 75 degrees. And my calculator is going to be very happy to tell me that that comes out at 6.47 meters. Right. So I have my x component, I have my y component. I'm running out of screen space, but I can write in component form. That 25.0 meters at 75 degrees is the same thing as the components, 6.47 meters and 24.1 meters. Once I have my vector in components, I can do things with it. So we already saw that we can kind of sort of add our components together, and that's exactly how it works. So if I have 2 vectors that are given in components, R1 is 3.85 meters and 17.9 meters, and R2 is 12.6 meters and 9.81 meters. And then I want S to be R1 plus R2. Well, with that, S is going to have an X component that is 3.85 meters plus 12.6 meters. And it's going to have a Y component that is 17.9 meters plus 9.81 meters. I can punch that into my calculator. I do have to be a little bit careful here. I'm rounding to the nearest tenth of a meter, even though some of these are given to the nearest hundredth of a meter. So I'm going to end up with components of 16.5 meters and it looks like 27.7 meters. Does that make sense? If you think about the picture that we saw previously on what it looks like adding some vectors together, I think it should make sense. Right? 3.85 meters, 17.9 meters, R1 looks something like that. And then we go from the head of R1, continuing onward, we get something that looks like that. So our total vector, if we take the straight line, is just straight through. And if I look at the components of the result, well, this is just the x component of R1 and the x component of R2. This is the y component of R1, and this is the y component of R2. So yes, it does look like geometrically we can just add things together and everything works exactly the way that we expect it should. That leaves us with just one question remaining. If I have my vector given in component form like this, well, we just saw that it makes a lot more sense in a lot of applications to talk about a vector as a magnitude and a direction. So can we work backwards? If we have the components of a vector like this, can we find its magnitude and direction? And the answer is, of course, yes, we can, right? That's the kind of question where the answer is clearly yes, because if the answer was no, the instructor wouldn't have bothered to ask it. All right, so we have 16.5 meters, we have 27.7 meters. Those are the x and y components of our vector, which means that they're going to be the two legs of our triangle. We're looking for this angle theta, and we're looking for the magnitude, which is going to be this distance here. A typical convention used in mathematics and in physics is that if s with an arrowhead is the vector, then s without the arrowhead is the magnitude of the vector. We can get the magnitude pretty easily. This is a right triangle. We know two sides. We're looking for the third. So Pythagorean theorem to the rescue. S squared is going to be equal to 16.5 meters squared plus 27.7 meters squared. If I punch that into my calculator, and then take the square root of that value. I wrote down 1040. I'm keeping all of the extra digits that are in my calculator and just hitting square root of the previous answer, which comes out as 32.2 meters. If you tried literally typing in square root of 1040 instead, it would come out as, well, 32.2 meters. If we needed one more significant digit, that would be off, and that's kind of normal. All right, the point of significant figures is that because I rounded this to 3 significant figures, if I round that to 3 significant figures, I should be in the same place. All right, so we have the magnitude of our vector. Now to find the direction, we're going to need to worry about that angle. Let's see, we have the two legs, and the relationship between the two legs of a triangle is the tangent. Tangent of theta is the opposite over the adjacent, which means that theta itself is the inverse tangent of the opposite over the adjacent. Although I do have to put a big asterisk on the equal sign here. In this particular example, that's going to work perfectly fine. If I take the inverse tangent of the opposite, which is 27.7, and the adjacent, which is 16.5, right, units are meters. Meters divided by meters cancel each other out. This is a unitless value, and that is important. If it were not a unitless value, we wouldn't be able to take the inverse tangent. I'm going to put my calculator on the screen real quick, maybe. Okay, my calculator camera is not working today. That's okay. Depending on your calculator, finding inverse tangent can be a little bit tricky. On my calculator, I hit the tangent button twice. On some calculators, you hit the second key and then the tangent button. But we want to take the inverse tangent of 27.7 divided by 16.5. My calculator tells me that that is 59.219, etc. degrees. I'm going to go ahead and round that to 59 degrees. That seems like a good place to do so. Right? I mentioned before there are rules for how to round angles using the significant figures. I'm not going to be that worried about it because we're going to try to stick with a consistent scheme of 3 significant figures for all of our distances, and that tends to put our angles to the nearest whole degree, and we'll go with that. It's just a little bit easier than having to think about it. The rules for rounding angles make a lot of sense when you're working in radian measure, but we're going to work in degree measure because it makes everything else make sense. So, one thing to kind of ease our burden a little. All right, so we have our magnitude, we have our direction. All that's left for me to do is to wrap this up by actually writing out the answer. Vector S is equal to 32.2 meters at 59 degrees. All right, now let's look at that asterisk. The problem with the inverse tangent is that it assumes that we're dealing with an angle in the first quadrant, and that's not always going to be the case. What if our resultant angle was over here? Or what if it was over here? Interesting thing. If I put my resultant angle over here, then that means that my x component is going to be something like negative 7.50 meters, and my y component is going to be something like positive 5.50 meters. Or if I put my vector over here, well, that means that my x component is going to be positive something like 7.50 meters, and my y component is going to be something like negative 5.50 meters. And if I take opposite divided by adjacent, well, I have 5.5 divided by negative 7.5. My calculator tells me that that's negative 0.733. Or if I took negative 5.5 divided by positive 7.5, I would still get negative 0.733. So the formula for dealing with inverse tangent loses information. It cannot distinguish between an angle here and an angle there. We need to do it manually. So there's a couple of different ways you can think about this. Mathematically, they all work out the same. The way I think about it is let's ignore the signs. Let's ignore whether the angle is positive or whether the lengths, let's ignore whether the components are positive or negative in the first place, and we'll just worry about the fact that this ratio comes out at 7.33. The inverse tangent of 0.733, my calculator tells me, is about 36 degrees. Then I want to take that 36-degree angle and translate it to the appropriate quadrant. So if I'm dealing with this vector in the second quadrant, the angle of 36 degrees is right there. But the convention of working with angles tells us that we want to measure our angle from the positive x-axis going counterclockwise. So that's my angle theta. And if you stop and think about things, remember that the distance halfway around the circle, from the positive x-axis all the way to the negative x-axis, is 180 degrees. We tried to go that whole distance, and then we got stopped 36 degrees before we reached the end of the line. So if I take the 180 degrees, that would be all the way to the negative x-axis, and subtract the 36 degrees where we didn't quite make it, we get that this angle theta is 144 degrees. We can do the same thing if we had that vector in the fourth quadrant. If we had the vector down here, well, the way we drew it, the angle of 36 degrees was right there. But we want to represent this as an angle from the positive x-axis going counterclockwise. And from the positive x-axis going counterclockwise takes us all there. If we went an entire way around the circle, my camera is doing some weird parallax thing, so I can't trace that out quite, but kind of like that. If we went all the way around the circle, it would be 360 degrees. We didn't quite make it that far. We came up 36 degrees short. So in this case, we're going to want to take 360 degrees minus the 36 degrees, and that's going to come out at 324 degrees. I didn't look at an example in the second quadrant because, in the third quadrant, because in the third quadrant we would have been dealing with two negative values, and two negative values divided gives you a positive result. But if we had something there, we still would have gotten this same sort of a reference angle, and maybe it would look something like that. In this case, things are a little bit different because it's not that we came up short of some convenient reference point, we actually went a little bit beyond some convenient reference point. Going halfway around the circle takes us 180 degrees, and then we went a little bit further. So in this particular case, we went 180 degrees, then we went another 36 degrees beyond that. Adding those together gives us 216 degrees as the angle there. I'm not going to go through examples in the other direction. If you have an angle that is large like this, like 216 degrees, and you're given the magnitude and direction and you're asking for the components, in that direction, things work fairly nicely, right? Take the magnitude times sine of the angle to get the y component, and it will automatically figure out whether that should be a positive or a negative value. Take the magnitude times cosine of the angle to get the x component. It will automatically figure out whether that should be a positive or negative value. That much is fine. It's when you're trying to go backwards, you have the components and you're trying to find the angle, that you lose information. So dealing with the arctangent, you have to be a little bit more careful. Dealing with sines and cosines, nothing to worry about. So I'm not going to go through a whole bunch of examples showing you that. I think this video has gone on long enough, so I'll wrap up with this one. Thanks as always for joining me. I'll see you next time.